approaches infinity, you have the 1/2, and you said u to the -1 over -1, right? Now you could change these, but I'm just going to keep waiting. Let me write this again. Limit as t approaches infinity. -1/2 where the u is in the denominator. Did I go there? And what's my two limits? Well, I'll put my u back. What was u? So I'm going to resubstitute. Absolutely. Some of you like to change the limits of integration. You can totally do that. There's your u. You could have changed these. I'm just showing this because some students like to just wait till the end, resubstitute what u equaled, and get it back in terms of the x's and those t's that we saw over there earlier. So I'll resubstitute. I get limit as t approaches infinity, -1 over 2 times parentheses, x squared plus 1. And the limits were from 0 to t. But Connie, you're right. In the end, I'm just plugging in a t in there, I'm plugging a 0 in there, and I'm going to subtract these. I get the limit as t approaches infinity of -1 over 2 times parentheses t squared plus 9 minus the limit as t approaches infinity of -1/2 0 squared plus 9. Can we do the easy part first? Negative makes a positive. What's the limit as t approaches infinity of any constant? The constant, well, what is it? 1 over 18, plus 1 over 18. Very good. Am I all right with that? Now what about this? I encourage you to approach that numerically.
There's a 0.
It's 0. Now love, you are so confident, you're like, that's going to 0. Oh, but it's negative. But we're like, what? -1 over a million. -1 over a trillion. It's just getting closer and closer to the number. This is converging. I think we saw it here too, didn't we? Looked like it was going to happen right there. This converges to 1 over 18. But it's okay if you just write 1 over 18 because the direction said what? Evaluate those that are convergent. And say my answer is 1 over 18. Look at this 2 out of the way. Ooh, good, Connor.
Is 1 over infinity always 0?
Yes.
So
1 over infinity squared is always 0. And what we're saying, you know, the language is I say, okay, the limit as x approaches infinity of 1 over x is always 0. And the limit as x approaches infinity of 1 over x squared is 0, but you can always think like that.
So like you can think like just plug in infinity.
Exactly.
Okay.
It really helps. Let's do some others. Like, you go, all right, well, this was 1 over, and this was t squared, but this was t cubed, or t to the 4th. These are all, it's just going to keep leaving a 1 up in the numerator. This just keeps getting bigger and bigger and bigger, and it's send it to 0.
Okay. Thank you.
And we're doing that numerically. Kind of, we're just thinking about it. Like, that's going to 0.
Anything over infinity, any constant over infinity is going to be 0, right?
So you think, yep, so you're like, even if it had what? Let's think of a really big number, 10,000. But this was just x squared down here. And someone wanted you to find the limit. As x approaches infinity, you are correct. We're saying, guess where this is going? That's a pretty big number in the numerator. But this is exploding towards positive infinity. So it's still turning to 0.
Negative infinity assumes the same, right?
Yeah, let's see. What if this was going towards negative infinity? Well, a negative number squared makes it what? Positive. It's still going towards 10,000 or a very, very infinitely large number approaching to 0. Excellent. The trouble is when there's no more denominator with x, and it gets where? It gets up here, like that. And you go, okay, now there's no more. This is over what now? And you get that, now where's this thing going? You know, I use positive because it has a square root, right? Where a square root of a value has to be positive, so we'll send it towards infinity. This is going towards infinity. Once it got up, that's what we're talking about, the antiderivative. You get that antiderivative, and all of a sudden it's up there. You're like, square root of x? It's going toward it. Even natural log of x, even though it grows slowly, it grows so slowly as x gets larger and larger and larger, still going towards it. Cool?
Could you change the bounds using the something?
You sure could? So I want to show that. If you want to change them right here, this is all we have to do. So now, u equal, let's start with a 0. What would that be?
9.
So you plugged in a 0 for this, now you gotta plug in this for this, and what do you get?
T squared plus 9.
And it looks funny, but of course, that's why I didn't write it. I didn't want this to bug anybody. You go, ugh, right? But it's still, in the end, it's gonna be right there for the student. They're gonna see it, right? But that's why I didn't substitute it early. I didn't want this to annoy anybody in here. I just kept waiting and waiting and waiting, and I resubstituted it here. Cool. Hey, before we do one of those other types of improper integrals where there's no infinities, but there's a 1 to 2, and maybe it's undefined at 2, the expression there, how do you set up a problem like this? This is number 13. All right. We can get it started. If you want to keep working the whole thing out, we can. But it's really the discussion of the setup. How do you start something like this? What if there are two infinities? X e to the negative x squared dx. Right? A good example for all this stuff, has anybody taken statistics? Few hands are going up. You know the bell curve, the normal curve? Did you know we always looked at area underneath it and we went towards what? You probably never saw it in your stats class, but you're thinking area in that bell curve that was centered right here. We usually went out only 3 standard deviations because 99.7% of data is within 3 standard deviations, but we really thought about it infinitely. Well, that curve, everyone, it's an improper integral when you think about it, but it converges to the area of 1.0. That's why we can do all the probability, because some probabilities go to 1.0 is 100%, right? So that's just somewhere like, wow, this stuff's even related to a statistics course. But this is kind of like that. How would you set this up? Because it has how many? 2 in terms of the limits, and we got to use this variable t. So what you have to do is, the setup, you got to do 2 portions separately, and then you sum them. So I'm going to do this. Then as t approaches, I'll start with this one, negative infinity, and I'm going to slice this in the middle. What's halfway between negative infinity and infinity?
0.
I could have sliced it at 1, but I'm going to use 0. It's very simple. I'll go from this t value now to 0. This is how we got to start the problem. Plus the limit as t approaches. Now I'm going to use the infinity, and I'll go from 0 to what? 0 to the. But you only have to do this if you have infinities, a negative infinity, and a positive infinity expression. So you have to work out this, get your answer. Work out this, get your answer. You'll be good to go. Just examine this closely. Integration by parts or u sub? Integration by parts would have been something like that. That's an IDP. Don't worry, Kate, they look the same. They look the same. The reason, see that power difference by 1? That's what's making this a u sub problem. And you let the u equal to what? Negative x squared. But this would have been on integration by parts. X e to the x. Same thing if this was x sine of x squared. U sub. And I think what gives it away, Kate, is that power difference by 1 integer. If that helps. Did anybody want me to work this? Oh, I got some people like, yeah, let's do it. All right, so this is going to be interesting. Now, you're talking about diversion. What if one part of these two diverges? Then stop the problem. The answer is what? Who cares if one side converges, the other side diverges? It automatically is going to do what? Diverge. So that's kind of cool. Sometimes you'll have to work one side and it automatically diverges. But if this converges, we're going to have to come over here and finish this up. Cool. So we'll work this all out. At least to involve the same u sub, right? Now let's do it. U sub, u equals the negative x squared with du. And let's divide out that negative 2. What do you get? Has anybody already gotten to the point you do u subs in your head? That's pretty good. That's really good. You've done them so many times. You just see this half coming eventually, the negative 1/2. So I'm gonna go back in here. Negative 1/2. This x dx got knocked out by just a u, right? I mean, negative 1/2 to u, and you got an e to the u. No, wait, I gotta write this again. Okay. Okay. No problem. I'll do it. All right. What's gonna be u? U. So I get negative 1/2 e to the u. So far, so good. Now I'm going to resubstitute, and then I'll put my original limits. What's the, if I resubstitute u, what do you get? Resubstitute, I'll get e to the negative x squared. I don't care with that? I'll do that. Limit as t approaches negative infinity. Negative 1/2 e to the negative x squared. I have to be really careful, all these negatives, they're all over the place. Negative infinity, you got a negative 1/2. We're getting all this, and then we're substituting what two values? I resubstituted a t and a what? A 0. Okay. So I get limit as t approaches negative infinity, negative 1/2 e to the, just to give me enough room here, I want to write on this side, we'll deal with this later. Limit as t approaches negative infinity of negative 1/2 e to the negative 0. Minus limit as t approaches negative infinity of negative 1/2 e to the negative t squared. Substitute the t, right? Which part's easier? What's e to the negative 0? 1. What's negative 1/2 times a 1? Okay, so we do the easy part first. You're just negative 1/2. This is the part we're all concerned with. We're not going towards positive infinity, we're going towards negative infinity of this expression. So, we're like, man, I need knowledge of the graph of e to the negative x squared. I wouldn't be so concerned about that negative 1/2, but the graph of y equal e to the negative x squared. Does anybody know what y equal e dx does? As you go towards this negative infinity? We can look at it. Anybody got a calculator? You can, but trust me, you can look at this numerically. I mean, I heard the calculator's coming out. That is totally fine, but I didn't want you to get too annoyed with that calculator. Be like,
Just a bell curve.
I might be able to do this. Well, you might even want to look at this Armando numerically. You and I are trying to subtract the limit as t approaches negative infinity of this expression. Well, if you plug in an infinitely large negative value here, it squares and becomes what?
Positive.
Positive. E is 2.7. So here we go again like before. Connor, what we were talking about earlier with these other expressions where it was like 1 over x squared, 1 over x cubed. This is negative 1 over an extremely large number. This half is converging. This is converging to 0. And we just looked at this numerically, right? Negative 1 over 2 times an infinitely large number. In the denominator, this is going to 0. So what did this part converge to? I'll put it right here. Negative 1/2. But we still have to take this answer and add it to what? This one right here. Now you want to work all this out? Yeah, sure. This problem has an interesting answer. That's already negative 1/2. Can I erase? Or maybe I could just leave everything up. Everything should stay the same except for my what? When I plug in the
Bounds.
bounds. So I can do that. Was everyone got this so far? If everyone's caught, we got that part. I'm going to leave all this up so we can do it again with this part. Except when I get to here, I'm going to go from t to 0, I'm going to change this to a positive. I'll do that. So I'll wait till you're all done copying. We got half of it. But this looks like that, everyone. This looks like this is going to converge too. I mean, we're dealing with the same thing. But it's all about a graph. You know, we got to be careful with these graphs. You know, I don't know. Maybe this end was going towards 0, but the other end's going towards infinity. So we'll still work it all out. All right, I'm gonna erase. Ready? That's -1/2. All I have to change now is what? The negative infinities are now what? All right, so I'm gonna change this, so I'm gonna go, all right, you're plus infinity, you're plus infinity, you're pos infinity, that stays the same, but now my limits are what? I'll use yellow. My limits are 0 to t. Well, then I'll erase all this. How's this play out? That's a pos infinity. I would get the limit as t approaches positive infinity of -1/2 e to the negative t squared, subtract the limit as t approaches positive infinity, -1/2 e to the -0. Start with the easy part. What's that number? That's -1/2, and what's the minus of a -1/2?
Plus.
So this is +1/2? Okay. I think you all see it again. Everyone see the negative exponent? What's going on? It's going towards 0, isn't it? You bet e to the x squared would have gone towards infinity. That's e to a negative t squared. That's 1 over e to the t squared. This again is going towards what? 0. Does everyone see that? If you have to, write in your notes. This is 1 over 2. This is right next door in the denominator. Yeah, I'll do it right now. Like, this is right here. That's going to 0. 0, maybe. So, hey, this is +1/2. So what's the final answer to this problem? This was -1/2. This is +1/2. What's -1/2 plus 1/2? You came out to be -1/2. This came out to be +1/2. The answer is -1/2 plus 1/2. Converges to 0. Finite area. 0 though. Oh, net area. Still with integrals. Can't you get the negative applied when it's underneath the x? So what probably happened to this graph? We probably had, we got that odd symmetry, right? That's exactly it. So did anybody look at this graph? You might have saw that with your eyes first.
It's a bell curve, but it's negative.
Oh, you got the graph? We can put it on the board and we should see, oh, why does this come out to be 0?
You got the graph going?
That's down there. Uh-oh, something happened with this. Because that would give something else, right? Oh, the x is missing.
No.
That's okay. We're going to graph that y equals x to the x squared. So hey, I'll delete this.
Second ins, you can just insert to that.
Oh, cool. I think I delete that whole thing. Just put an x in front of it. X e to the -x squared. We'll put this on the board. Everyone feel free to put in your calculator. X e to the -x squared. Let's see why this is coming out to be 0.
So,
It's an odd function. Yep, hit that graph. You might want to zoom in on it though.
I got the graph.
You got it? So it went like this, but what's going up there? Did it do something like this? He's got the graph too over there. It's like over here it did something like this, but then here it went like this. And it's an odd function, so yeah. What's going on? This was the -1/2, this was the +1/2. Odd function, what's the interval? 0. Cool. But hey, if you're thinking about statistics, flip this part of it up. 1/2 plus 1/2 would give you what number? Yeah, and you're thinking about, oh, I can do like this. It's almost like the normal probability curve, the bell curve. Hey, now we got to do one of these problems where you don't see the infinity. You get something like this. This is problem number 33. All right, it's got a 0 and it's got a 9. It's got a 1 over the cube root of x minus 1. This is number 33. Is this really an improper integral?